Hello everyone. In today's lesson, lesson 2, we are going to talk about static electricity. And just as a review from our last lecture, there are two kinds of electricity, static and current. This lesson is going to focus purely on the static form of electricity, and our next video lesson will focus on the current form of electricity. I put this slide up here kind of to serve as a review, but also to show you that if you guys are more graphic organizer or you want to do something like that, to remember there are two kinds of electricity, instead of writing just straight up notes, that there's a different way to do this, that you can do two kinds of electricity up here followed by a little branch system to get static and current. All right, and we will talk a lot more about graphic organizers as the units and this semester wears on. But to focus on static electricity here, which is what this lesson is, the key things out of this that you need to figure out, or that you need to make sure you commit to memory, is that static electricity is an electron buildup on a surface. So electron buildup on a surface. Make sure you understand that. That's all static electricity is. It's where electrons, remember those are the negative charged subatomic particles, when there's a whole bunch of them on a specific surface, okay, they start to build up and they build up and they build up and they get what's called a negative charge. Okay, that's static electricity, and we'll go into much greater depth as this lesson wears on. Static electricity is naturally occurring, for example, lightning, and is always direct current again. And then with your current electricity, they have a free-flowing electrons. They are man-made, and they can be either direct current or alternating current. And that's all I'll say on current for right now. All right, so let's dive in more specifically on static electricity. And again, the definition of static electricity is the buildup of electrons or electric charge on the surface of an object. And you've seen it, especially in the wintertime, where we have dry, colder air, because dry, cold air is a better insulator than warm, moist or very humid air. And you'll see that if you've ever been received a little shock, a little static shock, whether you touch someone or you touch a doorknob, basically what happens is when your shoes rub up against a carpet, especially like longer haired carpet like shag carpeting, it creates more friction. And friction is definitely needed for static electricity. Put that in your notes. You will see that later on as well. You must have friction to create static electricity, and that friction separates positive and negative charges. So what that means is it separates the electrons from one place to another. So you can see here in this diagram, all these negatives are the electrons, okay? And that means they've left the shoe and they've gone to here, okay, into the rug. And we'll talk about what this is in just a second, and that means that really is just what's called an electric potential difference. You can also see it down in this diagram with the balloon. You can see a piece of wool, and a balloon itself has an equal number of positive and negative charges, so they're neutral, and the wool also has a positive negative charges as well. Those are equal currently, those are neutral. Once you rub the wool cloth onto the balloon, the electrons go from the wool cloth onto the surface of the balloon, okay? And so now the balloon becomes negatively charged, right? And the wool cloth is positively charged because there's more positive charged ions than there are negative charged ions, all right? So in this case, this wool cloth becomes an electron donor, because it donated the electrons on it, and the balloon is an electron acceptor. I won't say much about these terms yet, but later on I will talk more in depth. I just wanted to introduce them. All right, so on this slide, the two big things that you need to make sure that you know, hands down, is electric potential difference and electromotive force, okay? Force being the key word there. So EPD, electric potential difference. If you think logically, all that really means is that something is different, and it isn't different right now, but there's a potential there, and it has something to do with electricity. All right, so EPD is the difference in electric potential. V stands for volts, voltage, which we talk about down here, between the final and the initial location when work is done upon a charge to change its potential energy. Now, you don't need to memorize this whole long definition. I just put this in here to give a very specific definition of what an EPD is. All an EPD is that between two areas, and I'll use my lightning cloud, my big thunder cloud here, that there's a big difference, right? All electrons, every electron on the planet wants to go to the Earth. Every single one of them wants to go to land. They don't like being in clouds. They don't like heights. They want to be on the ground, okay? So through the process of lightning, which we'll talk about how clouds get charged, which is what the top part of the cloud is positively charged, the bottom part of the cloud is negatively charged, and the ground becomes positively charged, which allows the electrons to escape to the ground from the cloud via lightning, okay? Now, you can see here that there are a lot more electrons than there are protons or positive charges, okay? So there's a lot more negative charges than there are positive charges here. That's a difference. That's an electric difference. Before the electrons come down to the ground, that's a potential difference. That's where we get electric potential difference from. It just means there's a lot more negative charges in one area than there are of another area. That's the difference, okay? Now, moving on to electromotive force. Force is a push or a pull, okay? So if you look over to the person next to you and you lightly push them on the shoulder, that's an electromotive force. Well, that's a force, okay? So you're applying force onto that person. They're moving in response to that, okay? So electromotive force is just the maximum potential difference between two electrodes of a galvanic or voltaic cell. Now, this portion of this definition refers to mostly talking about current and batteries, but we have electromotive forces in nature too, and specifically lightning clouds, doorknobs, even in balloons when you rub them with wool claws, all right? So the electromotive force is just the amount of force that the electrons move with. Now, you can have a slow thing like a 1.5 volt AA battery. 1.5 volts is the measure of that electromotive force, okay? So an EMF is a force. The more force you have, the more volts you have. And all a volt is, or voltage, is the amount of force provided by some kind of cell, whether that's a cloud or whether that's a battery, okay? Now, a 1.5 volt AA battery does not have as much EMF or electromotive force as a 12 volt battery. Does that make sense? The more volts you have, the more electromotive force you have. Okay? So EPD, electric potential difference, means there's more electrons in one area than another, and an electromotive force is the amount of force or push those electrons travel in between the two distances. Okay? And a voltage is just the amount of that force, the amount of force the electrons move with. That's voltage. Now, I talked a little bit about lightning, but I wanted to show you a real brief video. It's only a little more than 2 minutes long, and this is it gives you a visual of how lightning works.
As the Earth is heated by the sun, it produces lots of warm, moist air. Warm air rises. As it gains height, the moisture cools and condenses to form clouds. These clouds grow and merge into larger ones, rising all the time. Some of the water drops become too heavy for the updraft of air to lift and fall as rain. Are lifted by powerful air currents high into the cold upper regions, where they freeze into tiny crystals of ice. As the cloud hits the base of the stratosphere, it spreads out sideways to form the anvil shape typical of thunderclouds.
The clouds that make lightning are the largest clouds in the atmosphere. A big active cumulonimbus cloud is about as wide as it is deep, and they generate long anvils which extend horizontally in the prevailing wind aloft.
Some ice crystals build in size to form small hailstones. Scientists believe that as these hailstones fall back through the rising ice crystals, millions of tiny collisions occur. These collisions build up an electric charge, which is stored in the cloud like a battery.
A cloud is very much like a battery, but a battery with a much higher voltage than your typical flashlight battery. Not 1.5 volts, but 100 million volts.
But what scientists don't know is exactly how this electric charge generates lightning.
What remains a major meteorological mystery is how it is that ice particle collisions result in the generation of lightning. We're very much in the Middle Ages on that problem.
All right, so hopefully that was a decent introduction to how lightning works. Now let's talk a little bit about the specifics of the charges. I know that that video pretty much focused on how we get a charged cloud. So as those tiny as the hail falls and it hits the water and it creates those ionic charges, what we get is a lot of positive charges in tops of clouds and a lot of negative charge in the bottoms of clouds, okay? And that creates an EPD, an electric potential difference. And you can see lightning between clouds, as you, I'm sure, have seen in your lifetime. And that just means that there's an area of a lot of negative charges kind of close to an area of positive charges, okay? It's not an exclusive, like the top half of the cloud is positive and the bottom half is going to be negative. But you will see a big clumping of those charges. Okay, so positive charge up here, negative charge down towards the bottom. Now, the ground would normally have an even distribution of charges. It would have a positive charge, negative, positive, negative, positive, negative, something like that. It'd be very neutral, right? Now, like a magnet, like repels. So if I have two magnets and they have negative charge ends to them, they're going to repel in the opposite directions. If I have opposite charges, they are going to attract and come together and form a magnet or a magnetic seal, okay? So what happens is, as we get a bunch of negative charges in the bottom of clouds, these negative charges repel against the negative charges of the ground, and they start moving these negative charges away from a certain area on the ground, which then creates a positively charged area of the ground, which you see visualized here. Now, once we have a whole bunch of negatives up in the cloud and not many negatives in a specific area of the ground, we create an EPD, an electric potential difference. And when that builds up to a maximum point, we get a discharge, okay? And that discharge is when all of the electrons go from the bottom of the cloud and they come down to the ground to meet up with the positive charged ground. Now, the amount of force that these electrons travel with is the EMF, the electromotive force, okay? Now, the electromotive force of lightning is higher in the winter than it is in the summer. And the reason it's higher in the winter is because the air around the cloud is drier and colder than it would be in the winter months, or in the summer months, excuse me. So in winter months, we have cold, dry air. And cold, dry air is a better insulator than warm, moist air. Okay? So because cold, dry air is a better insulator, it has a better job of keeping those electrons together and away from going to where they want to go, more electrons build up. And when more electrons build up, we get more voltage. The more voltage we get, the more EMF we have, or the higher electromotive force we have. Okay? So that's how lightning basically works when it comes to charges. Now, like the video said, there are things that we don't know very specifically how they work yet. Science is an ongoing field of study. So how do we generate static electricity on man-made ways? We can use a thing called a Van de Graaff generator, which is what we have pictured here. Now, there are certain things that are absolutely necessary for static electricity to work. And this is something that you must know. I said it earlier in the lesson. I'll say it again. You have to have friction. Without friction, the two different areas can't be charged. You can't have a positive charged area and a negatively charged area. And that means you can't create an EPD, an electric potential difference. So with no EPD, no static electricity, okay? And to get EPD, that electric potential difference, you have to have friction. So you need friction to make it work. All right, so to generate static electricity, you need friction, and electrons have to move from one surface, so from one surface to another surface. And you can see in some cases that the electrons are visible in this form of what we call a man-made lightning bolt. All right. Now, there are two things that are necessary as well for static electricity to work. Those are electron acceptors. That's the object that accepts the new electrons. And electron donors. Those are things and objects that donate electrons. So going back a few slides here to this guy, we have an electron donor in the wool blanket, okay, because it gave up its electrons to the electron acceptor, the rubber balloon, okay? So electron acceptor are rubber balloons. Electron donors would be things like wool cloths. And those are the two things that we need to have. That and friction is what we need to generate static electricity. Now, electron donors and acceptors are placed on a thing called a triboelectric scale, okay? And a triboelectric scale is just, it's a ranking of different substances on whether they're more likely to become an electron acceptor, meaning a negative charged object or item, or an electron donor, something that is more likely to become positively charged, okay? And you'll see that we actually have a lab coming up that demonstrates the triboelectric scale. You'll see real life versions of them and you'll be able to work with them. We're also going to work with the electroscope, and that is just a very simple device to measure in a non-quantitative way, more of a qualitative way, the level on triboelectric scale for different substances. All right, so stay tuned on these two things. We'll talk about more in an upcoming lesson, in an upcoming lab in a day or two. All right, and then again, that is a picture of a Van de Graaff generator, and I thought I would show you another brief video on how a Van de Graaff generator actually works. Okay, so watch this.
The Van de Graaff's rubber belt winds around a Perspex roller. There are also some sharp metal points almost touching the belt. The Perspex roller rubs against the belt and goes positively charged. Negative charges rush through the metal points and try to jump to the positive charge, but they hit the belt instead and get carried up to the top, where they jump off onto the metal dome. They want to get away from each other, but there's nowhere to go. There's a metal globe connected to the sharp points at the bottom. Moving it closer almost completes an electrical circuit. So what happens next? The negative charges are still trying to get away from each other, so they jump across the gap. It's like a tiny bolt of lightning.
All right, so you saw briefly how a Van de Graaff generator works. The belt and the metal clip allow for that separation of charges. The belt will then transfer up electrons, and it depends on whether it's negatively charged particles or positively charged particles, depending on what substance you have at that bottom wheel. In the stuff that we're working with, it's negative charges, okay? But the negative charges transfer up the belt. They then transfer onto the metal dome, and when they've created a large enough EPD, electric potential difference, they jump over to something else, and they either go through, you can see this girl's hair, this one, where the electrons will actually spread out because they're like charges, and we'll go more over that in class. But you can see that in person with the electrons actually moving, and when like charges get close to each other, they repel. And you can see that in that girl's hair in the middle there, that the hair is moving apart because the electrons are negatively charged and they repel each other because they're like charges. Okay? And I believe, hold on, I think that's, yep. Oh, we've got one more slide, and that is our geek of this lesson, Count Alessandro Giuseppe Antonio Anastasio Volta. You may just learn Volta. I won't make you memorize the other 17 names this dude had. He was born in Como, Lombardy, Italy, to a noble family. He was not a count. He was credited with the development of the first modern battery. Make sure you know this point. It was called a voltaic pile. Okay, so make sure you know that. The unit of measure volt is named in his honor. Make sure you know that. That should be fairly easy since volt is very similar to volta. And again, volts are the measure of force the electrons move with. All right. He also discovered methane, which is kind of cool. So make sure you know at least these two. This one's a nice to know. If you do know it, fantastic. But make sure you know those other two. And that is the final slide of this particular video lesson. Your secret number of the day is 4. That is your video secret number. Thanks so much, guys. Do your homework, the rest of your homework, and I will see you in class.